Now that we've seen a couple of examples of non-defective matrices, let's pose the question, what then would a defective matrix look like? Here's an example of a defective matrix, and we are going to prove why it is defective. Here is 0, -3, 3, 6. Now on the surface, you might not be able to tell right away that this would represent a defective matrix. So what I'm going to encourage you to do is do the typical eigenvalue, eigenvector algorithm, and we'll see what happens. So we're going to be setting up the determinant of a minus lambda I is equal to 0, our characteristic equation. So subtracting lambda from the entries on the main diagonal, 0 minus lambda will just be negative lambda, and 6 minus lambda. The other two entries will stay the same. So calculating the determinant of this 2 by 2, we'll have negative lambda multiplied by 6 minus lambda minus -3 times 3. Sorry, got ahead of myself and actually did the multiplication. Distributing the negative lambda through and reordering appropriately, we're going to wind up with lambda squared minus 6 times lambda, and then minus -3 times 3 will become plus 9. That'll be equal to 0. When we factor this, it does factor very nicely into lambda minus 3 quantity squared is equal to 0. This tells us we have only one eigenvalue, but it has a multiplicity of 2. So we get lambda equals 3 with a multiplicity of 2. The multiplicity of 2 implies that when I plug in lambda equals 3, we should get 2 rows of zeros. We should get 2 free variables. Now let's see what actually happens when we plug in lambda equals 3. So we'll be setting up a minus 3i times v is equal to the 0 vector. Now because it's a 2 by 2 matrix, we're going to assume that v is a vector in R2. So I'm going to be subtracting 3 from the entries on the main diagonal. 0 minus 3 will give us -3. 6 minus 3 will give us 3. Then we'll still have a -3 and a positive 3 left over. Now good news is, it shouldn't take too much effort to turn this into reduced row echelon form, but you'll notice we are not going to get 2 rows of zeros. Rather, if I add the 2 rows together, I will get 1 row of zeros. And if I take -1/3 of the first row, I will get this. This is why this would be considered a defective matrix, because a multiplicity of 2 leads to an eigenspace that is only one-dimensional. We can interpret this as being v1 plus v2 is equal to 0, resulting in only one single eigenvector, or rather one single linearly independent eigenvector. Any other eigenvector would have to be a scalar multiple of this, which means that this is a defective matrix. So the long story short on this one is go through the typical eigenvalue eigenvector process, and if you wind up getting fewer linearly independent eigenvectors than the supposed dimension of the eigenspace, that's how you'll know that this matrix is defective.